Section 1.4 is solving equations. This is usually what people are ready for when they come to Algebra 2. They're like, I know how to do this. This is good stuff. So our objective, we want to be able to solve equations. Remember, you might want to take the bag off. If you don't have highlighters and colored pencils and that kind of stuff, you might want to take that bag right off of your desk there and grab some of those materials. We're going to solve equations. It's going to feel like stuff that you know. It should feel like review. And to solve problems by writing equations. Now that's going to be some word problem stuff, applications, but not a big deal. We're going to ease right into those, and hopefully you'll feel like, hey, I remember all this stuff. So a blank is a statement that two expressions are equal. I actually talked about this in one of the other videos. When we have equals, that's an equation. Again, think root words. A lot of the words that we use in mathematics, and we learn this in geometry. If you just look at the root word, you know what it is that we're talking about. So an equation, a little something like 1/2 x plus 5 equals 7/2. It's an equation. We have a left side to the equation, 1/2 x plus 5, and we have a right side to the equation, 7/2, and we want to know what value of x would make this work. And that's called the solution. So properties of equality that we use when we want to solve equations, reflexive. Again, if you think about geometry, reflexive, root word, reflect. Well, what does something look like when you look in the mirror? You get the same thing right back. You see yourself. That's what a mirror does. So that's a little silly A equals A. Now, why even bother with that one? Because it is kind of silly. Because if you are working on, and there's some math problems that could take you 3 days to solve, and at some point you need a new variable. Everything you did worked, but you got to a point where you're like, I need to introduce a new variable. How am I going to do that? Right here. You can introduce a new variable and say, hey, it equals itself, and away you go. Symmetric. Okay, root word symmetry. When you have symmetry, that means you can fold something over and you get the same thing on both sides. So A is the same as B, and B is the same as A, and you can flip those things around. So if A equals B, then B equals A. Again, think of a root word, and generally you can reason away. Math is logic. It really is. Transitive. All right, well, how are you going to pull this one off, Cedarholm? Well, transitive. T-R-A-N-S. Transitive. What else is a word I've heard something like? Well, transit. It's like busing. That's like when you go from home to school and then the bus takes you from school back to home again. That's what the transitive property does. It's a link. It's like a school bus route. That's what it is. So if A equals B and B equals C, then A equals C. It links those two together. It's like, well, and think of it as flights too. Sometimes you have to have connecting flights to get where you want to go. But in the end, where you started and where you end is what's important. Substitution is just that, substituting. So when we substitute, we replace a variable with something. In most cases, it's a number, but sometimes we have to replace it with a variable. And like it says in this case, if A equals B, then wherever we see an A, we can put a B. Wherever we see a B, we can put an A. And that's what vice versa means. We can interchange those two variables. So you're working along on a problem and you realize, gosh, I'm really close to solving this, but I still have two variables. In order to solve something with two variables, we need two equations. So you start to think, how can I get this down to just one variable? Chances are pretty good. You need to look around for something to substitute. You need to go back and see, okay, what did I say my variables were? How did they work? Addition. Pretty straightforward. We know from all the solving that you did in high school that as long as you add something to one side of an equation, you have to add it to the other side. You have to. Algebra is about balance, keeping both of those sides balanced. So to solve an equation, we absolutely can add, but we need to do it to both sides of the equation, both the left and the right. Same thing with subtraction. You can't get away with just doing anything with one side. It has has to be both sides. So if A equals B, then A minus C equals B minus C. So what are you doing with your highlighters or colored pencils at this point? Maybe nothing. Maybe every single one of these is something you're like, yeah, I know this. But maybe one of these was one where you went, oh, wait a minute. Yeah, I'd forgotten that one. Then you want to highlight that. So you go back to it later and you look at it again. So it just comes back to you normally. Multiplication, we do that. Sometimes we have to multiply by the reciprocal on both sides of an equation to get rid of a number that's in front of our variable. So if A equals B, then A times C equals B times C. If you multiply on one side of the equation, you have to multiply on the other side. Keep it balanced. Later on, we're going to find out that we could take logarithms, which is something brand new to you in second semester. But it's the same way even with logarithms. If you take the logarithm of one side, you have to take the logarithm of the other side. It's that balancing act that we do in algebra. Division happens all the time. You know, usually it's the last step we do is we say, okay, we've got 3x. How do I get rid of that 3 in front of that x? Well, we divide. But what we do to one side, we have to do to the other. So if A equals B, then A divided by C equals B divided by C. And Z cannot be 0. Don't flip the page yet. Didn't see that on any of the other stuff. None of the other ones said C can't be 0. So what's so special about division that C can't be 0? We can't divide by 0. So division is one of those things where we can have glitches, and we have to watch out for that in math. If suddenly we're dividing, we have to remember, hey, I can't divide by 0. In fact, if you try it on your graphing calculator, it's going to yell at you and say you can't do that. Error, can't divide by 0. So this is called a restriction in the domain. All right, so that's the fancy way to word it. The restriction in the domain, what does that mean to us? It means that you're telling somebody, use this formula for whatever you want, but there's one number you can't use it for. And in this case, it would be 0. So anything that makes our denominator equal to 0, we have to tell people, hey, there's a restriction on the domain here. All right, now we can flip the page. Solving an equation is finding all the values of the variable that make the equation true. We like it when it comes out x equals 3, x equals -7, where we get a one number answer and things are good. It doesn't always work that way, but we like it that way. So what we do is we use inverse operations to undo, because that's what inverse means, undo an equation. But here's what's important. We also have to use the order of operations backwards. So where we had please excuse my dear Aunt Sally before, now we have to start at the bottom and say let's undo any addition and subtraction. Then let's undo any multiplication and division. Then undo any of the powers. And then figure out those parentheses. Now generally we've got it solved by the time we get to the parentheses piece. But we literally use the order of operations backwards. So using the inverse operations to undo an equation, good example, subtract to undo addition. And like I said, these are going to feel pretty straightforward. So take a look at problem 1. It says x minus 8 equals -10. What would you do? Yeah, add 8 to both sides. Can you be certain your answer's right? How? Plug it back in. Make sure it works. Is -2 minus 8 equal to -10? Yeah. This is where you're taking the test and you go, I know I got that one right. You build yourself up a little confidence. And keep going. Take a look at the got it. 12c equals 18. What would you do? Divide both sides by 12. Sounds like a good plan. Done? What's left? We do have to reduce. I mean, that's a part of Algebra 2. We always simplify. We want to give our answers in the simplest form possible. So what are you going to divide the top and the bottom by? Yeah, 6. Most people look at it, think 2 right away, and then realize, wait a minute, I can use a 6 for that. Is that checkable? Sure it is. One of the things I love about equations. Put it back up in there. Make sure it works. So 12 times 3 halves is going to give you 18. Uh-oh. What does your instinct tell you need to do with this first? Distribute? Sounds like a good plan. Be careful. Remember that you have to take a negative 2 times everything in the parentheses. So negative 2 times y will give you negative 2y, but negative 2 times negative 1 will give you plus 2. Again, most common mistake made in mathematics. What are you doing next? Stare at it and hope it goes away method. It's still there. Subtract the 2 first? Sure. And then you said subtract the y? That's not the way some of you did this, right? Because some of you were taught always get your y's together first and always move the smaller one over to the other side, right? You think we'll get a different answer? We're following the rules. So what do we do at this point? Divide by negative 3. What do we get? 6. So, like I said, some of you learned, hey, let's add the 2y over here, let's add the 16 and deal with that way. You're going to get the same answer. And we're following the order of operations backwards when we do these problems. So we'll get the same answer. Oh, that looks a little scary. Yikes. Go ahead and do this one. When you're done, I want you to do what I call chicken wing elbow partners. You chicken at your desk, flap your wings, and people that would be closest to your wings, they're a chicken wing partner. Check in with them and see if they get the same answer that you do. And yeah, you could flap. It's a good way to start your day. Flap like a chicken. To do it the same way to get there. But it's those negatives that you want to watch out for. So what I noticed was people distributing. And everybody was being careful about that -8. Then we combined like terms so that we were simplifying the left side to see what was going on. So we've got this 6x here, and then there was a -6x here. Hey, that dropped out. That's pretty cool. These are gone. And then we had -11 equals 11x divided by 11. There it is. You know, that's how it's supposed to be done, and you were doing it. So now, word problem. Looking at the clock thinking, well, I hope we're almost done. She can't get this in. We can get this. The map shows distances between towns in miles. 46 miles, 44 miles, 37 miles. You and your friends drive together from Newtown to Essex. You drive first for a total of 40 miles. Then your friend drives 1.5 hours to reach Essex. What's your friend's average rate? Here's the deal. I'm not going to solve word problems like the book does, because if you want to solve them the way the book does and it's never been a problem for you, you can read right through that. I want to teach you new ways to do word problems so that you can think through them logically. Here's the way to do that. What are you trying to find? You're trying to find the average rate. Okay, so that would be like miles per hour stuff. So you go and look at this and you think, I don't see anything about miles per hour in there. That's not miles per hour. That's miles. That's time. What on earth are they trying to do to me here? Let's do it the cheater's way. You look at this picture and you say to yourself, what's the only thing that I can find for a total? How far did they go? That's what I can find. So I'm not going to be directly finding the average rate. I'm going to have to figure out how far they went. I'm going to have to figure out the distance. So we take 46 plus 44 plus 37, which I might not need a calculator for, but I know some are off. It might seem like a big task at this point. And there it is. How am I going to get something miles with the information they gave me? Oh, cool. They gave me one. You drove 40 miles. Excellent. You weren't the only person that drove, were you? Okay. Your friend drove. We have an equation that's about distance. They gave us time. Think of something that we know when we're supposed to use distance and time, maybe from science class. That's what we know. So instead of using distance, we can use rate times time. So I think, does that help me out? Do I know either my friend's rate or my friend's time? Do I know one of those? I know my friend's time. 1.5 times whatever their rate is. I'll use a little r for their rate. Will that find me my friend's average rate? Absolutely. Like I said, it's kind of the cheater's way. You look at the picture and you say, what can I get from that picture? I can get the total distance. So what I have to find and build up is that total distance. So now we'd use a little algebra. So what would you do first? Subtract 40. Then what would you do? And nobody came back from the summer and said, yes, I want to divide by decimals right away. Oh, I can't wait for that. There it is. 58. So let's be careful. 58. Good. Miles per hour. This was in miles. The information about your friend's time was in hours. Miles per hour. Page that we just could not get in class. So just to put a little summary together here of what we did. With this problem, the issue was we could not directly set up an equation to find that average rate. So what we need to do is think, what do I have? I mean, there's got to be something in this information that screams to me, hey, I can find this. And in this case, it was definitely the picture. We can see how far it's going to be from Newtown to Essex. So we're finding distance. And then we work through the problem and say, hey, fantastic news. We knew 40 miles, already done. You drove that 40 miles. But how are we going to figure out that friend's rate, thinking in terms of distance? And this little formula has to pop into our noggin. How do you get the distance? I can substitute in rate times time. And that, of course, left us with the R standing for the friend's average rate. And that's how we can get that indirectly. So, word problems. Keep chugging through them. Sometimes equations have a single answer, the one we just solved. We got an answer to that. We said, hey, this is 58 miles per hour. This is absolutely going to work. But they don't always work out that way. Some equations have no solution. Now, when are you going to know when that happens? You get done with all the math, and you get this statement, 3 equals negative 2. You double check your math, you've done everything right, and you realize that's not true. 3 does not equal negative 2. You're absolutely right. That is a false statement. That will never be true. So this will have no solution. If we see anything goofy like that, so 4 equals negative 10, 8 equals 7, that's how we're going to know that there is no solution. What it means graphically is that you have 2 equations that are parallel lines. But as far as the solutions when we're solving, we know that it's something that makes absolutely no sense. Sometimes all values make the equations true, and these are called identities. Now, identity is one way to write what has happened. You could also write infinitely many solutions. That means whatever number you put in for x, it's going to work. This you will know because you're solving away and all of a sudden you get 7 equals 7, 3 equals 3, negative 5 equals negative 5. Those are always true. So we have 2 things that can happen besides getting just one answer. Like I said, in the last problem, we had an answer. It was 58 miles per hour. That's one answer. No solutions is when your math leads you to a statement that is absolutely not true. But when your math leads to a statement that is always true, that is called an identity or infinitely many solutions. So let's take a look at problem 4. It says, is the equation always, sometimes, or never true? And your first thought is, do I have to do something different with this one than we did with the others? And the answer is no. So what we're going to do first is we're going to combine any like terms on each one of the sides. And that will give us 3x plus 4, because 3x it doesn't have any other like terms on the left-hand side. And then 11 minus 7 is 4. Over on the right-hand side, we have 6x minus 3x, which is 3x, plus 5. Just combining those like terms. And then we say, oh, well, I'll move this x over. I'm going to subtract 3x from both sides. And I will get 4 equals, whoa, 4 doesn't equal 5. Exactly. And that's because this equation has no solution. So we get that statement that makes absolutely no sense, and we know that it has no solution. Let's take a look at B. Similar in that we have to start by combining those like terms on each side first. So over on the left, we would have 4x plus 5, and over on the right, we would have 4x plus 5. Now, right away, that should grab your attention. You should go, wait a minute, those are both exactly the same. Wait a minute, that means it has infinitely many solutions. But let's just say you keep going. So you're still solving away. You're in the zone, and you are solving. And you get 5 equals 5. Of course it does. That's always true. So this is, you could either write down an identity, or you could write down that it has infinitely many solutions. Either one of those would be an acceptable answer. So for the got it here, I want you to go ahead and give these 2 a try and see what you can get. Pause the video and see how it goes. All right, as we work through this one on the left-hand side, we would distribute the 3 and get 2x plus 3x minus 12. And on the right-hand side, we would go ahead and distribute the 2, so that'll be 4x minus 12 plus x. Then we'd combine those like terms on each individual side, so this would be 5x minus 12, and over on the other side, 5x minus 12. And you actually could stop right now knowing that absolutely that's going to be true, Or you could take that additional step and see that negative 12 in fact does equal negative 12, and either write the identity or infinitely many solutions. Either one of those would be correct. For B, we don't have to do any distribution right away, but we do have to combine like terms over here on the left-hand side, and then combine like terms over here on the right-hand side. And then we go ahead and subtract 3x from both sides, and have 6 equals 4, which we know is absolutely never true. So this has no solutions. What that means is there isn't any value that we could put in for x everywhere that we see an x that would make this true. There is no solution. Graphically, again, this means that we have a pair of parallel lines. And that was as far as we needed to get today to meet what we were doing with our objective, the first part anyway, solve equations. We did have some solving problems by writing equations. We had an example that we worked through with that. But we're going to hang on for the literal equations. We're going to wait for that next week. And let me get you the assignment. So there is the assignment. For Friday. Lesson 1-4, day 1, page 30. Do 11 to 25 the odd, 27 to 32